So this is termination. So the further details about the protocol as well as its correctness can be found in this paper, Paxos Made Simple, and a copy of it is available on the module's website. So keep in mind that the presentation that we gave here in this lecture is adapted or was adapted to the standard setting of n-process consensus problem that we are considering. So in particular, we did not use these notions of separate roles of proposer, acceptor, and learner that is being used in this paper, Paxos Made Simple. So in fact, every process can be viewed as simultaneously playing all these three roles in our presentation of the algorithm. Okay, so other than that, so if you just can keep it in mind that all the three roles are actually unified in our algorithm, the way we presented the algorithm is identical to the one used by Lamport in this Paxos Made Simple paper. Okay. So to conclude, in this lecture we introduced Paxos, which is a widely used protocol for solving uniform consensus in the presence of partial synchrony. We presented this protocol in a fail-noisy model with eventual leader detector. So Paxos tolerates up to a minority of process crashes. And it can actually be shown that this failure tolerance is the best we can hope for in a partially synchronous system. And so Paxos algorithm is optimal in this respect. So the core of Paxos is abortable consensus. The abortable consensus never violates agreement, never violates safety, but may fail to terminate, so it may not be live. So if agreement is not reached in a particular instance of abortable consensus, then it returns a no decision, which is abort. Okay. So to assure termination, we take advantage of eventual leader detector that is available to us. And this eventual leader detector guarantees that once system becomes synchronous, then all correct processes will trust a single correct process as their leader, and they will do this permanently, forever. So once this happens, that leader will be able to execute multiple instances of abortable consensus in a row without being interrupted by other leaders executing concurrently, and therefore it will be able to eventually get its ballot to be high enough to be greater than any other ballot known to the process in the system, in which case it will be able to terminate. Okay, so in that case, abortable consensus will return a value and not an abort. Okay, so this concludes this lecture, and in the next lecture we will be discussing total order broadcast, which is very important primitive for implementing consistent data replication. And total order broadcast, or atomic broadcast as we called it in the initial lecture, is implemented on top of consensus. So for that reason we discussed consensus first, and now we can proceed to total order broadcast. Thanks for listening, and see you next time.